Hello. So finally, we're going to look at some new aircraft and new engine types. So in this video, we'll be looking at propeller-driven aircraft, and I'm going to have to bore you with a little bit of theory, but trust me, it'll be worth it. So firstly, I'd like to talk about the Cessna 172 that we all know and love. This Cessna is powered by a Lycoming, 4-cylinder, direct drive, horizontally opposed, air-cooled piston engine. Blimey. Allow me to explain what all of that means. Basically, this is a piston engine and it works very similar to a car engine. You have hollow cylinders inside an engine block. Inside of these, a mixture of fuel and air is ignited by a spark plug. This drives a piston inside the cylinder, which then turns a metal shaft running through the middle of the engine. This shaft connects directly to the propeller, so that when you increase the throttle, the propeller spins faster. You'll find this type of engine on almost all small trainer aircraft such as the Cessna. The other planes in FSX which have this piston type engine are the Mooney Bravo, the Extra 300 stunt plane, the Beechcraft Baron, the Piper Cab and the Douglas DC-3. Next, let's look at a more powerful engine called a turboprop. These engines work completely differently to their piston counterparts. To understand how these work, we need to have a basic understanding of how a jet engine works. So a jet engine consists of several main areas or parts. Beginning from the left, we have the intake where air enters the engine. The air is fed through a series of fans into a smaller area. These fans are known as the compressor because they compress the air. Behind that you have a combustion chamber where fuel is mixed into the compressed air. That fuel then ignites. After ignition, the fuel-air mixture expands rapidly and passes through a second series of fans called the turbine. The hot gas continues to expand and exits the engine at high speed through an exhaust nozzle, and this is what produces thrust. Now, coming back to the turbine, this is where a lot of power is generated. Like a piston engine, the turbine connects to a shaft running through the middle of the engine. This shaft also connects to the compressor and the intake fan. So as the fuel-air mixture ignites and spins the turbine faster, that in turn spins the compressor and the intake faster, allowing the engine to suck in more air, produce more power and more thrust. So that's a very basic look at a jet engine, but how does it work with a propeller? Well, the propeller actually sits away from the main engine and it connects to its own propeller shaft, and that is connected to the main engine shaft through a gearbox. The internal components of a jet engine can spin at tens of thousands of RPM, and if a propeller was to spin that fast, bad things would happen. So a gearbox is used to actually slow down the speed of the propeller. It's also worth noting that in a turboprop engine, a lot of the power generated by the turbine is sent through the shaft and gearbox to the propeller. The thrust effect of the exhaust gas is very low compared to a dedicated jet engine. Some of the turboprop aircraft in FSX are the Cessna Caravan, the Beechcraft King Air, and also the helicopters use a very similar type of engine to a turboprop. So apart from how they're built, let's look at some of the main differences between a piston and a turboprop engine. Piston engines are usually cheaper because they are relatively simple to design and manufacture compared to a gas turbine engine, i.e. a jet engine. That said, due to the nature of how each engine works, a piston engine does wear out faster than a turbine engine. While turbine engines are more complex in design, they end up having fewer moving parts, so there's less to maintain. With regards to performance, there's a very important difference to be aware of. A piston engine is quick at responding to your throttle input, so when you change the throttle setting, the engine speed changes quickly. A turbine engine, however, is slow to change speed, because it either has to gain or lose momentum to match your throttle input. Let's look at this example. Okay, so here we are in the Cessna 172 sat on the runway. So the way I'm going to test this is I'm going to run the engine from idle all the way up to maximum thrust and then back down to idle again. I'm going to time how long it takes to go from that idle, max, idle. So engine speed is down here, so we'll keep an eye on that. Okay, let's go in 3, 2, 1, full throttle. It's max throttle alert, down to idle. Okay, and that's about idle there. Okay, so let's try the same thing again with the Cessna Caravan. So if you keep an eye on this top row of instruments here, these are our engine instruments rather. So we'll do the exact same test. We'll go from idle to max to idle again. So in 3, 2, 1, full throttle. So that's maximum, down to idle. I'm keeping an eye on this torque gauge here, by the way. Okay, that's idle there. So you can see the difference there. It's not a massive problem, but it's just something to be aware of. Despite this lag, a turbine engine usually produces much more power than a piston engine, which allows the plane to fly higher and faster. Because turbine engines are more powerful, they can be used to fly larger planes. So looking at our two Cessna aircraft again, the 172 can carry up to 4 people, including the pilot, whereas the Cessna Caravan with a turboprop engine can carry up to 10 people. And having a larger aircraft means having larger fuel tanks, so a plane with a turboprop engine can generally fly greater distances as well. So looking at it like that, it seems that turboprops are much better. Well, not always. From my research, it seems to me that in the real world, when you need to consider things such as engine costs, fuel costs and maintenance costs, a piston engine aircraft is much better and much more efficient at flying at lower altitudes and over shorter distances, whereas turboprops are better for high altitude flying, long distance flying, and also for carrying heavy payloads, whether that be a large number of passengers or a lot of cargo. Now let's take a quick look at multiple engine aircraft. Now a multi-engine aircraft can use either piston, turboprop or jet engines. Most pilots learning to fly a multi-engine aircraft will start in something small such as a Beechcraft Baron, which uses piston engines. So using this plane as an example, let's have a look at some of the key differences compared to a single engine aircraft. So the most obvious difference is that you now have 2 engines instead of 1. This means that you have twice as many engine controls and instruments to keep an eye on. Here are the instruments for the left engine, and here they are for the right. If we have a look at the throttle quadrant, we have 2 throttle levers, 2 propeller levers, and 2 fuel mixture levers. Also looking at some of the other systems, you can see that we have a slightly more complex fuel system with a crossfeed function. Down on the switch panel here, you will find 2 engine start switches along with 2 alternators, one for each engine. So let's look at a general comparison between a single engine and a twin engine aircraft. So the first benefit of a single engine is that it's easier to fly. As I said a moment ago, you only have one engine to manage and less controls and instruments to keep an eye on. In the real world, having one engine also means that it's cheaper to buy and maintain a single engine aircraft. It uses less fuel and oil, and you only have to buy replacement parts for one engine, not 2. One of the benefits that a twin engine aircraft offers is that it has redundancy. What that means is that you have a backup plan. If one engine were to fail, you have a second engine that you can continue flying with. A single engine plane doesn't have that luxury if its only engine fails. Twin engine aircraft are also designed to cover greater distances, so they'll usually have better features such as a retractable landing gear, anti-ice features, or a more spacious cabin for passengers. With these features though come some more complex systems. For example, you need to think about synchronizing the engines and propeller speeds when flying, and also using 2 alternators to power the electronics. Also in the real world, you need to go and spend extra time and become more educated to learn and become certified to fly a multi-engine aircraft. The last topic I want to talk about is propellers and how they work. So imagine you have a 2-bladed propeller here, and imagine that it's sat at one end of a block of jelly. When you begin to turn a propeller, it will actually start to pull itself into the jelly, if you can imagine that. Think of turning a screw into a piece of wood, for example. It's the same effect. It's this screw-like motion which allows the plane to move forward. Propeller blades are actually shaped like little aerofoils or wings. This allows them to better direct the air as it hits the propeller and create thrust. Now, to make the propeller more efficient, you can alter what's called the propeller pitch. This basically means the angle that the blade is sitting at. The propeller pitch can be changed during different stages of flight to make the engine perform better and become more fuel efficient. This is controlled in the cockpit using the blue lever that we saw on the throttle quadrant earlier. When the blade is close to being in line with the rotational velocity, this is known as having a low propeller pitch, or a fine pitch. This allows the engine to run at high speed and is mainly used for stages of flight which require the best performance, such as takeoff. When the blade is angled more steeply, this is having a high propeller pitch, or a coarse pitch. This is generally used at higher airspeeds, when the aircraft is cruising along, for example. There is one more setting that you might come across, and that is a feathered pitch angle. This is basically when the blade is turned edge on into the airflow to provide very little wind resistance. This is mainly used if the engine fails, because it reduces aerodynamic drag. So that's pretty much everything I wanted to cover in this video. If you'd be interested in seeing some demonstration flights with different aircraft, following checklists for example, then let me know and I can record some bonus videos. In the next video we'll jump into some jets and look at everything all the way up to a 747. Hope to see you there, thank you for watching, and I'll catch you later.